In chemistry, the molality, B, of a solution is defined as the amount of substance of solute, divided by the mass of the solvent. Origin: the earliest such definition of the intensive property molality and of its adjectival unit, the now deprecated molal, appear to have been coined by G. N. Lewis and M. Randall in their 1923 publication of Thermodynamics and the Free Energies of Chemical Substances. Though the two words are subject to being confused with one another, the molality and molarity of a weak aqueous solution happen to be nearly the same, as 1 kilogram of water occupies 1 liter of volume at room temperature, and the small amount of solute would have little effect on the volume. Unit: the SI unit for molality is mole per kilogram. A solution with a molality of 3 mol per kilogram is often described as 3 molal, or 3m. However, following the SI system of units, the National Institute of Standards and Technology, the United States Authority on Measurement, considers the term molal, and the unit symbol m to be obsolete, and suggests mole per kilogram or a related unit of the SI. This recommendation has not been universally implemented in academia yet. Usage considerations: advantages, compared to molar concentration or mass concentration, the preparation of a solution of a given molality requires only a good scale. Both solvent and solute need to be weighed, as opposed to measured volumetrically, which would be subject to variations in density due to the ambient conditions of temperature and pressure. This is an advantage because, in chemical compositions, the mass, or the amount, of a pure known substance is more relevant than its volume. A contained measured amount of substance may change in volume with ambient conditions, but its amount and mass are unvarying, and chemical reactions occur in proportions of mass, not volume. The mass-based nature of molality implies that it can be readily converted into a mass ratio, where the symbol m stands for molar mass, or into a mole ratio. The advantage of molality over other mass-based fractions is the fact that the molality of one solute in a single solvent solution is independent of the presence or absence of other solutes. Problem areas: unlike all the other compositional properties listed in relation section, molality depends on the choice of the substance to be called a or solvent in an arbitrary mixture. If there is only one pure liquid substance in a mixture, the choice is clear, but not all solutions are this clear-cut. In an alcohol-water solution, either one could be called the solvent. In an alloy, or solid solution, there is no clear choice and all constituents may be treated alike. In such situations, mass or mole fraction is the preferred compositional specification. Relation to other compositional properties: in what follows, the solvent may be given the same treatment as the other constituents of the solution, such that the molality of the solvent of an N-solute solution, say BO, is found to be nothing more than the reciprocal of its molar mass, MO. Mass fraction: the conversions to and from the mass fraction of the solute in a single solute solution are, where B is the molality and M is the molar mass of the solute. More generally, for an N-solute 1 solvent solution, letting B and we be, respectively, the molality and mass fraction of the ITH solute. Where μ is the molar mass of the ITH solute, and WO is the mass fraction of the solvent, which is expressible both as a function of the molalities as well as a function of the other mass fractions. Mole fraction: the conversions to and from the mole fraction, X, of the solute in a single solute solution are, where MO is the molar mass of the solvent. More generally, for an N-solute 1 solvent solution, letting Xi be the mole fraction of the ITH solute, where XO is the mole fraction of the solvent, expressible both as a function of the molalities as well as a function of the other mole fractions. Molar concentration: the conversions to and from the molar concentration, C, for 1 solute solutions are, whereas the mass density of the solution, B is the molality, and M is the molar mass of the solute. For solutions with N solutes, the conversions are, where the molar concentration of the solvent CO is expressible both as a function of the molalities as well as a function of the molarities. Mass concentration: the conversions to and from the mass concentration, I solute, of a single solute solution are, whereas the mass density of the solution, B is the molality, and M is the molar mass of the solute. For the general N-solute solution, the mass concentration of the ITH solute, II, is related to its molality, B, as follows. Where the mass concentration of the solvent, I0, is expressible both as a function of the molalities as well as a function of the mass concentrations. Equal ratios. Alternatively, we may use just the last two equations given for the compositional property of the solvent in each of the preceding sections, together with the relationships given below, to derive the remainder of properties in that set. Where I and J are subscripts representing all the constituents, the N solutes plus the solvent. Example of conversion: an acid mixture consists of 0.760.20 mass fractions of H2O, where the percentages refer to mass fractions of the bottled acids carrying a balance of H2O. The first step is determining the mass fractions of the constituents. The approximate molar masses in kilogram per mole are. First derive the molality of the solvent, in mole per kilogram. And use that to derive all the others by use of the equal ratios. Actually, BH2O cancels out, because it is not needed. In this case, there is a more direct equation. We use it to derive the molality of HF. The mole fractions may be derived from this result. Osmolality. Osmolality is a variation of molality that takes into account only solutes that contribute to a solution's osmotic pressure. It is measured in osmoles of the solute per kilogram of water. This unit is frequently used in medical laboratory results in place of osmolarity, because it can be measured simply by depression of the freezing point of a solution, or cryoscopy. Relation to apparent properties. Molality appears in the expression of the apparent volume of a solute as a function of the molality B of that solute. For multi-component systems the relation is slightly modified by the sum of molalities of solutes. References